All right, welcome back to Lean Together 2026. Uh, at this point, we have Salvatore Mercuri speaking to us about the formalization of Fermat's last theorem, or at least some progress on it so far.
Yep, thanks very much. First of all, thank you very much for the opportunity to speak here. I attended my first Lean Together last year, so it's really nice to be able to come back and give this talk. I'm going to be talking today about the project to formalize Fermat's last theorem and some progress that we've made over the past year and a bit, specifically in an area of the project that we call the bottom-up component. And I guess it goes without saying that this is joint with a significant number of people. This has been a big community effort over the last year and a half. I went through GitHub to try and find who contributed. So this might not be fully accurate. So please do let me know if you think your name should be on here. But these are the people that I saw made PRs in this particular part of the project. So about 26 formalizers there, and then obviously there's lots of support from various people on bumping MathLib and removing upstream results and just giving nice ideas for formalization that have helps things massively across many areas. So today, I guess my talk, a quick plan, I guess it's sort of going to be like a funnel. I'm going to start really at the top level of Fermat's last theorem, and then I'm going to keep zooming in to components until we get to a point where I can actually do some maths and talk about some of the formalization that we did there. So that's the main structure of the talk today, and then I'll obviously finish up by talking about where we got to and what we're hoping to do in the future. So that's the plan. So first of all, I guess the overall FLT project at the moment, let me give you a quick, so we're all on the same page, like what Fermat's last theorem actually is. It's the statement that if a, b, c, and n are positive integers and the exponent n is greater than or equal to 3, then this equation can never be satisfied. So of course, for n equals 2, that's just the Pythagorean equation, which we've known for millennia that has infinitely many solutions. And it turns out if you increase that to 3, then actually this is never true. And so Fermat posed this in 1637, and famously it's taken, over 3 centuries for us to fully prove this in generality. So this was by two papers of Wiles and Taylor-Wiles in 1995. Of course, the special cases were proved much longer ago. So Fermat himself, I think, proved the n equals 4 case, and that's also in MathLib. That's been there for a few years actually. And then the n equals 3 case came later, and that's also recently I see has been upstream to MathLib. There has been recent progress in formalization for higher cases, I suppose, where the case where n is an irregular prime. This was fully formalized by Ricardo Brasca and many others in a paper last year. But of course, the fully general proof for all n requires the machinery of Wiles and Taylor-Wiles, and this is the content of the FLT project is to formalize this approach. It's going to be a modernization of the original approach that Wiles and Taylor-Wiles took, but it's along the same lines of proving modularity and deducing a contradiction. So that's what the FLT project is about. It started in late 2024, and I suppose this is a phase of the project that lasts for 5 years, and who knows what's going to happen afterwards. But this is a 5-year phase, I suppose you can think of it as. And so the overall project at the moment sort of breaks down into two halves. The one half is what we call the top-down formalization, and so that's I suppose this is what you really think of when you think of proving Fermat's last theorem. It's going to be the Wiles-Taylor-Wiles approach of modularity theorem. And it's top down because this is sort of going backwards. We're constantly reducing the Fermat's last theorem to results and eventually down to modularity theorem and getting that contradiction. It has a kind of a caveat to just for feasibility, I suppose, that any proof that was known by December 31st, 1989 will not be formalized, but the statements will be there because they're needed. But the proof won't be formalized, so they'll be assumed with a sorry. And I guess this goes to saying this is way beyond, I guess, the current capabilities of MathLib. It's not going to be upstream in the near future. So that's sort of top down. We have this barrier of results that are known in the 1980s that will be stated but not proved. And then sort of I suppose the other half is what I mean by bottom-up formalization. That's what this talk is gonna focus on. And that has quite a different flavor. Still, it's still very important stuff, but it's really more graduate level material, and it's really close to what's in MATLAB at the moment. Of course, it was also known in the 1980s, much of this material. So I'll talk a little bit about the distinction between sort of why we're formalizing this and not other things. And we aim to get this in MATLAB. This is designed for upstreaming as well. So that's kind of the rough overview of the FLT project. So I just mentioned that the bottom-up stuff is known in the 1980s. So why don't we just assume that, I suppose? And there's a bunch of reasons. There's no hard like clear delineation between them, but just some reasons here why we might want to do that. Of course, feasibility is a big thing. There are many results that were known in the 1980s, but whose statement even is going to take a long time to prove. And actually, the formalization of those would be themselves multi-year formalization projects. So, I mean, here's an example of something that's known in the 1980s, and you can sort of immediately see from the statement that we're very far from being even able to state that. So that's sort of one necessary condition, I suppose. But I put also that maybe it's a question of centrality. I don't know how convincing that is, but one of the things we really focused on in the bottom-up formalization was the Adele ring, and that sort of appears everywhere in the proof of FLT. It's sort of a really fundamental object, and so it sort of makes sense to build the basic API of that up and have that. And of course, sociological. So more people can get involved in the bottom-up formalization project. People want to get involved, and as we've seen from that large contributor list, like it's been a big community project, and not everyone has the time to get the expertise required to do top-down formalization in this project. So, and it means that we can help to develop MATLAB as well at the same time. So that's sort of a vague, I suppose, sort of reason for why we might want to do some things as bottom-up formalizations and not others. Um, and so let me give you an overview of the project, and more sort of more visibility on that. So this is the breakdown of the bottom-up project that I'm talking about today. It's not all of the stuff that we've done in I guess bottom-up FLT. There are a couple of other projects but they're independent, and one of them is already in MATLAB. So there's a project on Frobenius elements, and there's also another project on Heck operators, which we could also think of as bottom-up projects. I'm not talking about those today. This large project that I'm talking about today is the goal of this was to prove that a space of quaternionic automorphic forms has finite dimension. And in order to do that, we had to prove something called Fujisaki's lemma, which is sort of an adelic version of the finiteness of the class group. So there's some space of double cosets is finite. And those obviously requires quite a lot of theory from the Adele ring, and this comes directly out of MATLAB because we have the Adele ring there. And on the other side, we also needed a theory of sort of what we call Haar characters, which are kind of scaling factors of Haar measures, which again we have in MATLAB. And so we had sort of these different components to the project. People sort of worked in different parts. And we've got quite a large sort of for MATLAB folder as well of stuff that we think is immediately ready to go back into MATLAB. It's sort of the right generality. And so overall of these sort of components, we have a total of around 15,500 lines of code. And that sort of breaks down like this into the project, into the different components. We got about 296 definitions. So just just over half of those, just under half of those were in the MATLAB folder. Likewise, theorems, 972, 26 contributors who I listed on the front page. And then, yeah, I calculated a De Broglie factor using compressed file sizes of the lean files with the blueprint tech files, and that was about 5.4, which is sort of quite high. But if you take out the full MATLAB folder, then you get a 3.08. So some idea of the significant chunk that is in that full MATLAB folder there. So hopefully that gives you an idea of sort of the scale of the project and the work we've done there. I'm going to now zoom in again onto the Adele ring subproject. That's the part that I spent most of my time working in. So I'm going to focus on that as a case study to show some of the material that we did and some of the issues that we faced there and how we were resolving those. Right, so the Adele ring is if you've not encountered this before, it's a key object that's appeared throughout the proof of FLT. It's really fundamental across many areas of modern number theory. Somehow it's the right generality in which to think of automorphic forms. It has sort of You can see it on the right there. That's the Adele ring of the rational numbers. And what you do here is you're really taking all the completions of the rational numbers that exist, and you're just whacking them together into a huge infinite product. So you have the Archimedean completion there in the reals, and then for every prime p, you have the p-adic numbers. And then you put some restriction on that big infinite product. So there's a prime there. And that restriction sort of just means that for all but finitely many places, your element is actually in the p-adic integers. And that's sort of really important because this gives us a nice topologically small enough space, even though it's a massive infinite product. And so you can see from the definition that it's built out of local components, but it also contains the rationals embedded within it. So it has this kind of global component as well. So this sort of gives us the right way of thinking about automorphic forms as both being local and global. And you can see the definition of an automorphic form there from the FLT document. And in many modern areas of Langland's program, you'll see similar automorphic forms are defined idellically. And so here we have the automorphic forms actually is a function on the general linear group of the adels of Q. So just the very definition of, one part of the modularity requires this object. Similarly, I've just defined it for Q there, but you can also define it for any number field, and that's really the generality that we're working at in this project. And so when you're thinking about a number field, the Adele ring of K is, again, you can think of it as the set of all the Archimedean completions and then products with all the non-Archimedean completions. And so all the Archimedean ones is called the infinite Adele ring, and all the non-Archimedean ones go into an object called the finite Adele ring. And I suppose confusingly with the naming, the infinite Adele ring is actually a finite product, and then the finite Adele ring is this big infinite product that we again restrict. And we do this restriction to make it interesting topologically. And in particular, it makes it into a locally compact topological ring. I guess some history of in MATLib it exists as number field Adele ring. The first formalization of this was by Maria Inês in 2022 and was then upstream to MATLib at the finite Adele ring was, and then I finished this off in 2024. So that exists there, but we're still missing some kind of the most fundamental properties that we'd need for Fermat's theorem or really any application of the Adels. And so it's locally compact topological ring. That's really what we get from doing this restriction. It contains K, just like AQ contains Q, but that's a subring that's discrete and co-compact, so you can quotient with it and get a compact group. And then I suppose the thing that I'm going to focus on for the rest of the talk, and actually the thing that took most of the time in this project, is defining this base change isomorphism. So this is the idea that if you have another field L, that's a K algebra, and then you can sort of you can lift the Adele ring of K up to the Adele ring of L in a very powerful way. And also backwards, I suppose you can go from the Adele ring of L to the Adele ring of K. And this is an isomorphism it's a homeomorphism, but it's also algebraic. And I'll talk a little bit more about what that means in the next few slides. This is really powerful because in our example, we often work with number fields K. And so actually what you can do is you can reduce a lot of questions about the number field of K down to just down to Q by using base change. Yeah, this is really a huge part of the Adele ring subproject is just going into defining this base change map. So let me give you an idea of how we did that. I suppose in itself, it was also defined in a bottom-up approach. So because we can define it at the level of a place and then we can build it up to the Adele ring. And so I'm going to focus mostly on the infinite Adele ring because that's a bit easier. And the setup here is that we have number fields L and K, and L is a K algebra. And so we take V to be an infinite place of K. You can think of this as, well, it's an equivalence class of absolute values. So you can also think of V as a function on K into the reals. And then we're going to take an infinite place of W, an infinite place of L, such that if you restrict it to K, you get V back. So we say that W lies above V. And what we did in FLT is we defined a separate type there called extension. So this is sort of a subtype of infinite place L that restricts down to V. And then you can also then think of the completions of K and L with respect to these two topologies that V and W define. And so all of this sort of, apart from an extension, these all exist in MATLib. So that's the setup. And then what we get from this is that the ring inclusion going from K to L that we get from the algebra assumption, that's actually uniformly continuous, and that is what's coming from the fact that W lies above V. And so what we can do then is we can lift that to a uniformly continuous ring inclusion on the completions. And so then you can think of the completions having the algebra structure as well. Um, so then at this point, it's quite easy to just define the map from L tensor K into LW. On this, what this looks like on pure tensors is L tensor X, you just take the multiplication of L with the image of X under this inclusion. And so that's just the definition of the function. So it's an L algebra map with respect to the left algebra, which is the default algebra in MATLAB on tensor products. But if you think of it also as the right algebra, then actually this is also KV linear. And this idea that these sort of base change maps have two sets of scalars is going to be really important throughout the rest of the definition. So that's just a algebraic map. It's not topological yet. And then you just take the product of those to get a map that goes into all the LW that lie above V. And then this turns out to be an isomorphism then. And so this is sort of the hardest thing to show here is that this map is surjective. And then that really boils down to weak approximation. So the fact that L is dense inside the right-hand side allows you to prove surjectivity. And then injectivity follows because both sides have the same KV dimension. So this is the first instance where we're seeing that it's useful to think of this map also as KV linear. But actually, the most important reason why it's useful to think of this as KV linear is to do with the topologies. So I'm going to do a quick detour into how we define the topologies on the tensor product. So I think at the very start of this project, I think we defined the topology on L tensor KV quite ad hoc. We sort of defined it through an isomorphism of L tensor KV into some finite product of KVs, and then we were inducing a topology using that. Which was fine, and that's the topology I suppose you want to give it. But the problem with that is that we had to keep doing that at every level. So as we see when we go through whichever base change might be thought of, we had to keep defining a topology, and then we had to keep reproving things with that topology that it had continuity and things like this. And so the module topology is something that kind of solves a lot of our issues with that. So it was suggested by Will Sawin on a Math Overflow post by Kevin. It's now in MATLAB. And what is the module topology? Well, it's the finest topology that makes scalar multiplication and addition continuous. So R here is a topological space that's acting on A, so A is an R module. And this turns out to be the right thing to think about. It has a really nice property that every R linear map between R module topologies is continuous. And so then the module topology that we can give on the tensor product is the KV module topology. Of course, when you think of this tensor product as having the right algebra. And then we get continuity for free then, because we have this scalar property of the KVs on there. So then it's just automatically a homeomorphism. Provided that, well, the left-hand side, we've given it the KV module topology, and then you just have to prove that the right-hand side has the KV module topology as well, which turns out to be not very difficult. And when I talked about the ad hoc topology, where we were thinking of it as the product topology of KVs, it turns out to be the same as this. So if you pick a basis, then the module topology, and it's finite dimensional, then the module topology is just the product topology. So that's the idea. That's the idea with the module topology. And so now we can quite easily talk about these maps, these isomorphisms as being homeomorphisms as well, so long as both sides have the module topology. And so that's a strategy going forwards. So now we have the bottom level there. That's what we sort of showed in the past few slides. And now what we want to do is we want to lift that up to the infinite Adele ring. And so K infinity here, if you recall, is just the product overall of the KVs as the infinite places vary, and likewise for the L infinity. So this lift is quite straightforward if you only care about the L algebra map and you don't care about continuity and you don't care about the other scalar. So this is just the first thing is by definition. The second isomorphism, you just take the product out, and then you apply the isomorphism we've shown below it to each factor, and then you just have a fiber equivalent, sigma fiber equivalence happening in the last isomorphism. And that's just the infinite Adele ring of L. So algebraically, this is pretty standard. The issue is that, well, we want this to be continuous, and so we want this to have a second set of scalars. And what's the set of scalars that we want to give it? Well, the left-hand side of this map will be given the K-infinity module topology, and we can easily show again that the L-infinity has the K-infinity module topology. So somehow we want to lift the KV scalars of that map up to a K-infinity scalar, which is sort of not so trivial to do. It's not so easy. And it turns out that what you want to do there is what you want to happen is that the K-infinity action on L-infinity should somehow be determined by the fibers of the restriction function. Or in other words, the action of K infinity on L infinity is constant on those fibers. And so we've defined a class here that's sort of compatibility, I suppose, for doing this operation called pi fiber y small that just says exactly this. And so if you can either assume that pi fiber was small holds, or you can show it how it holds, and then immediately you can lift the KV scalars to a K infinity scalar map. And then again, we get continuity for free because of the module topology. So that's how the lifting happens on sort of, I suppose, the infinite Adele ring side. I unfortunately don't quite have time to talk about the finite Adele ring, but this is, suffice to say, this is a lot more complicated because we have an infinite product and then we have to worry about restricted products and all this stuff. But that's there as well. And then, of course, once you have these two isomorphisms, you can combine them at the top level to give you the isomorphism that you want on the Adele ring. So that's how we define the base change. Hopefully that gives you an idea of the construction. And then many of you might have noticed already that we might see an issue if we start lifting algebras up. So what I want to talk about now is an issue we faced with diamonds when we did this. So um, there are still, hopefully soon there were, cases of global instances of the form. We're assuming that L is a K algebra, and then we're going to globally construct some algebra on some transformation of K and L. We also faced issues with the scalar tower as well. And so, for example, we define globally the algebra of W completion over V completion, and likewise for the infinite Adele ring. Um, and so these cause diamonds because when K equals L, these somehow should have the identity algebra, and we've given it something that is not definitionally equal to the identity algebra, although you can prove that it is. It's just not definitionally equal. And so we found this to cause lots of timeouts at some point, as you might expect in advance. And so the resolution in progress for this, and hopefully this is a good way of fixing it. I'm not really sure if this is the best way, and we still haven't really fully fixed this yet. But the idea here is that because this algebra is okay, because W has a separate type to infinite placeout, it's a subtype, so this doesn't really cause any issues. But one issue we face, for example, and there's many others, is when we lift the infinite L ring, so we don't have this sort of type separation happening. And so instead, one option that we've proposed is to just assume this algebra wherever it's needed. So when we're defining, for example, the base change of the infinite L ring, we'll assume this instead. And then you have to then also assume things like pi fiber y small and some other things as well to make sure that you can do that lifting operation. Whereas previously we just proved this. And at some point, we can't get away from actually defining these algebra instances. So we do construct them at some point, and we do it towards the end of the sub-project. And then when we do that, we scope them. So if you need them, then you can open scopes them. And then this does fix the issue. So we have sort of a mixture of type separation and sort of scoping and using assumptions. This does sort of reduce the issues that we did have there. So I'm very curious to hear if other people have other proposals for this. There's been lots of discussions on Zoom already, I know. So that's hopefully that gives you a quick insight into some of the formalization that we were doing there. It's just a small part of the bottom-up project, which of course is a part of the overall FLT project. And to finish off, I wanted to talk about where we are with this and where we're going. So the formalization we have is actually complete. So as of I think last week, so very recent. So the main theorem that we wanted to prove is that this space of weight two automorphic forms, the quaternionic, are a finite dimensional k-vector space. And you can see the axioms there. There's no Soriax anymore. We have merged 109 Mathlib PRs that have the FLT label with them. I think there's probably more than that because I've definitely merged some and forgetting to put the FLT label on there. And we have lots open. So there'll be more from me and many others, I think, to stream all of this work in the future. Not sure how long that's going to take, but we'll try our best to get that in. We've got plans to write a paper about this particular theorem and all these projects. And then I think I'm not really sure if there's going to be any further bottom-up components, but for sure the top-down formalization will be a major focus going forward, since that's going to be it's going to be a lot of work. So yeah, that's everything from me. Thanks very much for listening, and happy to take any questions.